I'm Ted Selker, and I manage a group called User System Ergonomics Research at IBM Almaden Research Center. And today I'm going to tell you about power supply design in my usability group. And more I want to focus on the design approach that we take. Often we have competing ideas and philosophies that we work out by doing all of them and having them compete as we're doing the work. So it all started when one day I was giving a demonstration to an executive about the pointing stick, and this track point 2, which is in our products now, he was really enjoying. And what he enjoyed most about it, he said, was that it got rid of this gangly mess that is the mouse in his briefcase. So he went out of the room and he came back a few minutes later all excited, and he said, can't you get rid of the power supply too? It's a big gangly mess too. And I had been thinking a little bit about why this thing was so big, and I had a couple of ideas. I said, well, you know, you don't have to have computer grade power, blah, blah, blah. And in fact, because of who he was, people put a lot of pressure on me to go think about that. How do you get rid of this cord, for example? What about this away completely? We could just put in something that plugs it onto the wall. Was the heart of the power supply, a new kind of a transformer we invented. Maybe the power supply itself could be replaced with a smaller chipset that would allow it to be much smaller. And finally we thought of maybe we could think of a new way of making a power supply where there's no transformer involved at all. And so all of these things got built, and we had a lot of fun doing it. And the next few minutes we're going to take some time to go through each of these designs.
The electricity that comes out of the wall is called alternating current, or AC. This voltage rises, falls through zero, and then rises back again 60 times per second. The current IBM notebook power supply converts the AC electricity into 14 volts DC electricity. This is what the IBM notebook computer needs. First, the AC voltage goes through a bridge rectifier. This flips the negative voltage and makes it positive, making a waveform that looks like a series of humps. Then a capacitor stores electricity when the voltage is high and releases it when the voltage drops, smoothing out the humps and giving a more consistent output voltage. We then reduce it with a transformer, but transformers only work when the input voltage is changing. We first chop up the voltage into a series of pulses with a switching device to drive the transformer. This is where we get the name switching power supply. After the transformer converts the power to 14 volts, we rectify and smooth it for final use in the computer. To account for load and input power variations, which would change the output, a feedback controller detects variations in output voltage and signals the switching device to compensate for them.
Hey Ted, look at all this stuff I brought from the attic. I got transformers here, I got old circuit boards.
In a couple of general conversations, an old college buddy, Bob Kelly, told me about published ideas that no one else I had talked to was aware of. When I tried to talk him into working here, he said this stuff was just a hobby. He was a computer scientist. Well, he finally succumbed to my pestering to come here and begin some very productive research, like building a transformer in the shape of a power cord. A summer student, Jason Jacobs, calculated that our early designs could never be useful. We played around with different ideas and came up with one that was theoretically as efficient as any transformer.
All the time, and I'd like to try it.
So instead of doing the donuts for a transformer, like a bunch of donuts that we put the wires through, we could like put it on like a skein of yarn thing, and then wrap each of these things like the donuts around it.
Yeah, we could wrap the donuts around the yarn like a label on a skein of yarn.
Right. Oh.
A transformer normally consists of wire coils wrapped around an iron core. I came up with the idea of surrounding the wires with an iron donuts instead. Using whatever he could get his hands on, Bob came up with a wrapping technique to make them. Our tests showed that donuts improved transformer efficiency nearly 10 times. Our transformer, then, could be the basis of a cord-shaped power supply.
This power supply that IBM makes, what do you think of the one that was in the L40SX anyway?
Well, it's got air in it. It's almost as, I mean, like, look in there. There's all air, and look at all that inductive stuff.
This power integrations chip. What's cool about the power integrations chip?
Well, it's somebody had a good MOS process, and they found that they could integrate virtually all the electronics on just one chip.
So we were able to design and build a 1 by 2 by 3 inch power supply that was based on the power integrations chip. In this space inside this notebook, there's space for a floppy disk drive. This floppy disk drive space, when it was removed, it'd be nice to put a power supply in there. So we started thinking, how could we fit this thing in there? And the first thing to notice is this big capacitor. Notice that capacitor is as big as, well, it's probably a third of the volume of the power supply. We could take the capacitor out. The power supply would only produce power 85% of the AC cycle. This is okay because portable computers have battery backup.
Anyway, I keep being interested in this snipping business.
I thought to myself, in an AC signal, we go from 0 to 110 or 220, back to 0, back to 110, back to 0. But it goes from 0 to 20 and from 20 back to 0 4 times. And these areas here actually are low voltage. Wouldn't it be nice if we could use those, which end up being 15% of the duty cycle, and use this to charge a battery? Why do we need computer grade power just to power a battery?
I mean, it's getting close to getting ready?
Yeah.
Jeez. How do you sense that you're at the second place?
Well, there's this chip here. It's the LM10. It has a voltage reference in it.
Oh yeah.
And a comparator.
You see, in a normal transformer, you have some sort of a coil and a physical separation between the input and the output. That's what they always want in safety land. So what we do is another idea, which Bob Kelly and I worked out together. Have 2 batteries, not 1.
So this is pretty much the other part of the circuit.
So it can be charging one half of the batteries while we're running off the other one.
Cool. Anyway, we have the switching thing that goes back and forth between the batteries. And we have the charger, and then we have the slicer. But you got to go back up to finish up this graphics project.
Yeah, I have to go back to Oregon and finish my project, so...
It's really nice that you could take some time away. I'm sure they hate me. Oh, well. You know, I'm going to see if this great friend of yours, Joe, could maybe finish this thing. What do you think, Joe? What do you think of this thing?
Oh, I think it's a brutal yet elegant idea.
So how are we gonna get this pass transistor that he's talking about to turn on?
Transistor? I think a power FET would probably work better.
And so when it came time for me to really have to produce something that was more refined, I was desperate for a good electrical engineer. And when I met Joe Betts, I was convinced that maybe I've met the best electrical engineer I know.
Ted, it's sort of ugly, but it's actually quite beautiful. It works.
So you got this thing charging the battery, and you're saying it's going to work at 110 volts?
Well, it works at 125. Figure it'll work at 110.
Anyway, we got rid of it. There's no capacitors or inductors here.
There's no inductors. There's a tiny capacitors, but
cool.
There's a whole cloud of components. Well, if you put them in surface mount stuff, it sort of disappear.
Yeah. So basically, we just got to get rid of the heat there, and we're done.
Yeah. Oh yeah. Well, yeah. Now that it works, it's going to be much less interesting to work on.
Would you please make me one?
Really?
Are you kidding me? In the past few minutes, you've seen us show you a menagerie of design alternatives that we've been exploring, trying to improve the usability of power supplies. And really, it's been more than just focusing on some set of requirements that somebody's given us. It's been more an exploration and a playful pursuit of ideas, many of which cannot happen together, but all of which give us a family of design alternatives that could make the usability of a future computer much better.